So here we're going to make a linear model using some data that we have here. So we're going to start with the simple linear model by giving x some values. So we're going to have x going from 1 to 6 and modify with these numbers that are somewhat positively correlated with x. We've got 6 of them there because we need x and y to have the same number of numbers. If we define x and then define y, we look at the correlation between them using firstly the correlation of x and y. So we see there we have the correlation. The R value is 0.91. That also means that if we want the R squared value, we just need to multiply this to the power of 2. So you can see the R squared is 0.82. If we look at the correlation to test that gives us more stats, including the t value. So if we want to transform our correlation coefficient to a t value, we see there, and its degrees of freedom is n minus 2. So its degree of freedom is 4. And we see the confidence interval as well. So we should probably note that too. So there's a fair amount of noise with this data. So we're looking at really 0.36 to 0.99. Then we look at the linear model of x and y together. So you see there we have x on the right and y on the left. And y tilde x is the way you rewrite it, not x tilde y. So you see here for our old model, we have a different slope and intercept. Here we see the intercept is minus 0.23. So you write that in there, minus 0.233, and the intercept is 0.9. That model indicates that we have 0.9 by x. And then we have minus here, minus 0.2333. So that indicates the point at which x passes the intercept. So we can plot this as an O plot. So we can plot x and y together. That might be useful. X and y. And then we're going to have a larger text size and maybe a color to be red. We might add a grid as well. So you see there we have our plot. What we might do is just pan out by modifying x-lim to be 0.7, and then y-lim, we're also going to change that y-lim to be minus 1,7 as well. And that way we can kind of get a sense of where the intercept is. That's minus 0.2. So we can imagine there'll be a trend line running down here across the x-axis at x equals 0. So we can add that trend line, and that's called the outline function. And that uses this linear model function inside there as a direction. And we're going to change the alignment maybe to be slightly different and the line type as well. So that we can see a different color. Let's call it color blue. So it's more clear. So if we do that there, we can see a dotted line, and the point at which that's this line across this x equals 0 indicates the intercept. I will see the slope there has a value of 0.9. That would mean if we did a new value here in our array of x's of, let's say, 0.5, we could infer that we would get a new value which would be equal to 0.9 by 0.5 minus 2.33. And that was 2.169. So you can see there, if we zoomed in this diagram, if we had a value of 0.5 for x, that's where that would cross the x equals that would where it would cross the y equals 0 value. You'll note as well that this linear model is quite different if we put it the wrong way around. So if we did it the wrong way around, y tilde x, we would get the wrong values. So we'd have x, this intercept for y, but that model will be quite different because there we're putting y is equal to b by I plus some intercept c. So this would not be correct. So if we looked at this model, and let's say we wanted to plot an outline based on this model, if we did that for x tilde y, which again is the wrong way around, and we made the line black, with maybe a different line type, and try plot it on this diagram, you'd see that this plots on the wrong point. So you see this trend line, it happens to be relatively parallel to the y tilde x one here, but it's incorrect. You see that that's wrong. What we'd need to do is do a plot for the other way around, y comma x, like that, and then add that trend line on there, and that would match that particular data set. But that's not really the way we want to articulate things. So note that this is the wrong way around. that we shouldn't really do things this way in terms of our particular model here, although you may have variables where you're not clear on which is the independent and dependent variables. So just note that. Okay, so we can say more about our model here if we get a summary of our model. So this will tell us more that we'll discuss later, but that can tell us more details about our model, including the formula we used to do it, and also give us you can see here the estimate of the intercept and the estimate for the slope, and then other information there, including the t-value we had before and the p-value corresponding to that t-value for the slope as well. You can also see here that the multiple or squared value is listed there, as well as other information that we'll discuss later. So try question 1 on your own. Make your own example of 2 variables that are adjusted to achieve an R value of 0. Plot the data and add a line of best fit, and try to use the code above as a way of trying that out.